Howdy, this is the RF Mapping Rover team. We are a senior capstone project here at Texas A&M. So currently there are no indoor navigation systems commercially available that utilize Wi-Fi RF signals. We believe that a machine learning algorithm can interact with the RF environment and control an autonomous vehicle to predict its location. In the future application, we believe that it could help visually impaired people navigate indoors. Our design requirements were we needed an antenna that collected 2.4 and 5.8 gigahertz signals, greater than 50 signals per location, a database that collected the data from the Pi with a response time of less than a second, the rover receiving commands from the Pi with a response time of less than 10 seconds, and a percent error of data set greater than 80%. We broke the project down into 4 systems for our 4 members. The first was the rover, which utilized the motors, the motor driver, and the rover movement program. Then there was the database that used the Google Cloud database with the MySQL database. The antenna subsystem, the RF subsystem that took in the signals and then put it into the database. And then the machine learning algorithm that used the k-nearest neighbors algorithm to sort and control the rover. So for the vehicle subsystem, we used a Raspberry Pi to communicate with a Pixhawk via Mavlink. Since the Pixhawk didn't natively move a vehicle without GPS or RC signals, we tricked the Pixhawk into thinking it was receiving RC signals through a bit mask. The RF subsystem utilized a Huzzah board that outputted a 2.4 gigahertz signal, and it collected the signal using an omnidirectional antenna built into the Raspberry Pi. We filtered out that data using Wireshark and then sent that data to the Google API database. The database subsystem will transmit the collected data from the RF subsystem into a cloud-based SQL database through a proxy. The data is then filtered and sent to the machine learning algorithm to be processed. The machine learning subsystem imported the data set, split the data into a training and testing set, then ran it through a k-nearest neighbors algorithm using the 4 nearest neighbors. In the end, we were able to get the rover to successfully identify its location with about 70% accuracy. We were able to collect and filter the useful data using both omnidirectional and patch antennas. The outdoor collection had a much higher accuracy and there was less noise and reflection. The indoor collection was possible with non-beamforming antennas, or Huzzah boards. Future goals include integrating a form available to market, such as a mobile app, looking deeper into beamforming solutions, and being able to start outdoors and transition into indoor navigation. This is a video showcasing the rover working indoors. As you can see, this is the Pi that's interfaced directly onto the rover, and there's 2 LEDs there. That's the Huzzah board we set up, and as you can see, the rover just moved forward. And essentially this is fast forwarded, but it's showing that at this location it's collecting data from all 4 Huzzah boards, and it's basically the LEDs correspond with which one it's collecting so that we can monitor that. And as you'll see, once it collects it, it'll move forward, as you can see right here. And right now it is cycling again through the 4 access points, as can be seen on the LEDs kind of switching. As you can see here, it's reached location 5, our preset location point, and it just recycled through, meaning that it knows where it's at. So this shows our final results. It shows the output of k-nearest neighbors, and as you can see, about to be highlighted. It thinks it's at location 5, which is where it stopped, and this was correct.